graph networks.
Hi, can you hear me?
I can hear you, yes.
Okay.
Yes, and the slides I can see as well.
So, hello everyone, my name is Cenk Tuysuz. I'm a physics master student at Middle East Technical University located in Ankara, Turkey. So today I will be talking about our work titled A Quantum Graph Neural Network Approach to Particle Track Reconstruction, which is a collaboration between METU, CERN Open Lab, and GLONET. I divided my talk into 3 parts. I will briefly talk about particle track reconstruction and the TrackML challenge. And then I will talk a little bit about HepTrackX project, which is an old project. And then I will talk about our work, which is the quantum graph neural network approach. So as you have heard many times today, the high luminosity upgrade of LHC will bring many challenges to particle track reconstruction. And as number of collisions increase, number of tracks will increase, and the current algorithms are costing us worse than quadratically. So we need better algorithms to do better physics, and everybody's investigating what we can do better. TrackML challenge was one of these endeavors to introduce machine learning experts into the fields so that they can bring new ideas to how to solve this problem. So in this work, we also use the TrackML dataset. The HepTrackX team, in part of their work, introduced a GNN approach, a graph neural network approach to solve this problem. On the bottom left, you see a detector layout, which consists of the barrel and end caps, barrel layers and the end caps. As you see, when we have both the barrel and the end caps, the model gets a little bit complicated compared to only having the barrel region. So they omitted the end cap parts and stayed with only the vertical lines to simplify the model. And on the right, you can see a part of the TrackML detector model. And we also follow the same idea from HepTrackX team, and by only using 8, 13th, and the 17th layers of the detector. So their model was a graph neural network, taking an event, converting that to a graph, then processing it with a series of edge and node networks, then taking the tracks as outputs. Their model was scoring pretty good. You can see the scores on the right. And we hope to achieve similar results by using quantum computing techniques. Speaking of quantum computing, some of you might have heard before, quantum computing is a new way of computation that introduces us a new way of computing, and it can provide us some speed ups in certain problems, such as prime number factorization, solving linear equations, and most importantly for our case, machine learning. So in the literature, you can find many papers on quantum classifiers and how to do quantum machine learning. Here you see a very basic example. On the right, there is a quantum circuit that consists of 4 qubits. And with this circuit, you can do classification with the very famous MNIST dataset, and you can achieve pretty good results with this circuit. So in our work, we want to introduce this kind of quantum neural networks into the HepTrackX graph neural network. As you see on the bottom, we have a very similar network compared to HepTrackX. We switch the edge networks to quantum edge networks and the node networks to quantum node networks, and I will explain them in a couple of minutes. Continuing with the preprocessing of the data, we use the TrackML datasets, and we apply very loose cuts to this data. And then we divide the data to create segments, 2 8s in eta and to 2 in z direction, and to obtain a subgraph like this on the right. Since these simulations are pretty costly, we only use 1% of the TrackML data. And below you can see a histogram of 100 events after this preprocessing. As you see, we still keep the symmetry in phi, and also you can see the detector geometry in the histogram for R. Then we use the cylindrical coordinates, since our detector is a cylindrical detector and it has cylindrical symmetries. And you can see here that a single subgraph, which is a 1/16th of an event. And from the track ML data, we have the ground truths plotted in red and our initial guesses for the tracks in blue lines. So how can we convert a neural network to a quantum circuit? On the left, you see a very basic model where the black lines are our detectors and the red dots are our hits. So for each hit, we have 3 coordinate points in 3 dimensions. And we convert these 3 points for each node to an angle. We map these coordinates to be between 0 and 2 pi, and using a rotation gate, we rotate the qubits to have this rotation angles. Then we have this 3 tensor network circuit, randomly initialized, and then when we run this circuit, we get a measurement result of 0 or 1. The parameters here you see in the red boxes are our training parameters that we train. And these are, as you do in a deep neural network, randomly initialized, and you try to learn these parameters. So putting on this, we want to construct a quantum edge network that has both this classification feature and also can add up hidden features. In this quantum network, we are adding hidden features by increasing the number of qubits and by adding additional qubits to the system with a very simple additional input network. That input network takes a node and computes a randomly initialized new hidden feature. And in this example, you see only a hidden dimension of 1. But you probably seen in classical networks that most networks have many hidden dimensions, up to hundreds, maybe 200s. But in quantum networks, this is pretty costly. So right now we are sticking up to hidden dimension 1. But if we can get to faster simulations, we can use more hidden dimensions. Similar to the node network, here you see a similar portrait of hits. This time we have the node of interest in the middle, and we are using the information of the neighbors. So for each option, we need to create a new circuit that we run inside this quantum node network. So for a single option we have here, we create the circuit on the right, and we run the circuit, then take the node information and add it to this green quantum node net box here. Then you can see the overall structure again here. We start from the subgraph. We use the input nets to create hidden dimensions. Then we execute our quantum edge network to get edge features. Then we feed this information to quantum node nets and recurrently iterate this process. And in the end, we again execute the quantum edge network to obtain edge informations. If we have a look at how to train a quantum network, it is pretty similar to how you train a neural network, but there are, of course, additional steps. So in a quantum circuit, when you run a quantum circuit, you would either get a 0 or a 1, but this is not very useful for us. So therefore, we need to use some quantum state tomography techniques. Here we use the simplest of them. We just run the circuit n times, then take the average of the outputs, and this gives us an edge being, the probability of an edge being a true edge or a fake edge. Then these averages are used to calculate an error, then a loss from the ground truth data. And then we calculate the gradients for the quantum circuits using a parameter shift rule. And then we update these parameters with the formula that is used in most deep learning algorithms. Then we repeat the process until we get our wanted accuracy. Here you see our first results. On this plots, we have 3 different runs with different iterations of edge networks and node networks. On the orange line, you see the best overall result. But you would expect that as we increase the size of the network, the network with the greater size should perform better. But since our network is pretty simple and only uses a hidden dimension of 1, this is not the case. The network with the least complexity is performing better here, but this should be inverted when we have a more complicated network. On the right, you can see how the AUC is changing with the updates. On the axis, we have the updates, and the plot is made to fit a single epoch of data, which was 1% of the tricanal data. So we see that for 3 of the models, we get close to AUC values of up to 0.8, which is pretty good for a very simple model. And here you can see a very simple comparison between classical networks and the network that I showed you with hidden dimension 1. So we see here that increasing hidden dimension improves the performance on both of the plots. So we expect to see better results when we can execute our circuits, execute the quantum graph network model with higher dimensions. So to conclude, we still have many things to explore, but initial results are promising, and we are pretty optimistic to get better results. The things that we want to explore more is using more layers, more iterations, and introducing more qubits, which means more hidden features, and also trying out different quantum circuits with different architectures, and also increasing the 1% data to full scale. But these are all stacking up because the simulation times of quantum networks are very limited. And the results I showed you were run up to maybe a month, and which really prevents us from debugging the network pretty fast and doing fast development. Before wrapping up, I'd like to thank to my contributors as listed here. So thank you.
Thank you. Are there questions to Cenk? I'm just wondering, when you say this takes so long, you run this on an emulator, that's why it takes so long, or it takes so long to get access to a real quantum computer?
No, currently we are only using simulations, and these circuits are pretty big for simulations. When we have a quantum circuit with 12 qubits, you need to calculate matrices of 2 to the 12. The size of 2 to the 12 by 2 to the 12. So that takes some considerable amount of time. And since at each update, you need to run the circuit multiple times to calculate the gradients, it takes really long times.
Okay. But I assume on a real quantum computer, this would be very fast.
It would be faster than this, of course, but currently there is no way to run this in a real quantum computer.
Okay. Okay. Are there more questions or comments? I do not see anything. Then thanks again for your contribution.
Thank you.
And we go on with Marianne with